So one of the most commonly used numerical summary for location is average, or it's also called mean. And generally we represent average or mean by X bar. So for example, if you have number of cell phone minutes used last month and you have the data for 5 samples, so 500, 300, 200, 8 and 200, then you can easily find the average by adding everything and dividing by how many you have. So we have 1, 2, 3, 4, 5. So if you add, you get 2000 and divide that by 5. So your average is 400 minutes. So if your data is in minutes, this will be 400 minutes. One good thing about average is that it is based on each and every data point. It includes in its calculation every data point. But there is also a drawback of including every data point, and that is like if one of the values becomes very high, your X bar will obviously also indicate a higher average. In some situations where you have skewed data like skewed histograms, so there it is more useful to make use of another measure of location called median. So to find the median, you can arrange same data in order. So minimum 200, then you have 200, 3, 5 and 8. The middlemost value is 300, so that's the median. Now if you have like instead of odd numbers, you have even number of data points. For example, say you have 1, 3, I'm already putting them in order, so 7, 7, 8. So now you have 2 data points in the middle. Whenever that happens, you take the average of the two. So median will be 5 plus 7 by 2, which is 6. Median can be used in situations where your data indicates there is a lot of skew, whether it is rightly skewed or right skewed or left skewed. And one more thing you can notice is that median is more stable than average. Suppose instead of 800, if this last data point was say 80,000, very big number compared to all the remaining 4, still median will be 300. So it is not affected by extreme values, whether on the lower side or on the higher side, so it is more stable. Let me take one example from garment industry. So suppose there are two popular sizes and somebody makes histogram based on the data, and these are like how many items got sold in a certain period, and you get this kind of histogram. And suppose this is about 5.5 and this is about 6.5 in terms of some kind of size. So now if you take average of this data, your average will be somewhere in the middle at about 6. And if you use the average and decide to make only these many clothes of this size, so it will not sell because there are not much demand here. So maximum demand is at 5.5 and 6.5. So actually they should be making more of these two instead of 6. So in these situations, obviously mean or median will not work. What you need is mode, which is basically highest frequency. The data point which occurs more often with maximum frequency is the mode. In fact, this histogram you can say is bimodal because there are two modes. So you can obviously have more than one modes in a data set. Another measure of location is, popular measure of location is percentiles, which divides data into 100 parts. If this is the range of your data from 0 to 100 and somewhere here you have 10, if this is the 10th percentile, it basically means less than that you have about 10% of the data points, and more than that you have about remaining 90%. So that's the meaning of 10th percentile. Now to calculate a percentile, there's a formula you can use, I equals P by 100 times N. N is the sample size, P is the percentile. So there are two rules associated with this. So one is, so if you calculate I and whatever you get is not integer, you can maybe underline that, round up. And then the pth percentile is the ith value, or I can be integer. So if it is an integer, the pth percentile is the average of ith and I plus 1th value. Suppose we use this data. Obviously, to find a percentile also we need to arrange this data in order. So this becomes 200. Now let's say we are interested in P equals 10, 10th percentile. So calculate I. So 10 by 100, because P is 10 times N. So you have 1, 2, 3, 4, 5. So 5 data points. And you get 0.5. So first rule says if I is not integer. So obviously 0.5 is not an integer. So we round up. So this becomes 1. So it says round up, and the pth percentile is the ith value. So 10th percentile is the ith value. So I is 1, that means first value. And first value in the arranged data set is 200. So you can say 10th percentile equals 200 minutes. We can take one example of the other type. So suppose P equals 20. We are interested in 20th percentile. So calculate I. 20 by 100 times 5 is 1. So now we got an integer. So if I is integer, then you can say pth percentile is the average of ith and I plus 1. That means first and second value. So first and second value are actually both 200. So your 20th percentile equals, so you take the average of the 2, divide by 2, you get the average is 200. So this is still 200 minutes. So it need not be the case all the time. It might be different value for different data sets. Now another measure of location is called quartile, and as the name indicates, this divides the data into 4 quarters. Just like a basketball game, you have 4 quarters. So first quarter is 25% of the total time, and so on. So if you have this range from 0 to 100, and this is in the middle, and if you divide this into 4 parts, such that this becomes 25, this is 50, this is 75, and this is 100. So this is called first quartile, and this is your second quartile and third quartile. Now second quartile is the quartile like to the left of that you have 50%, to the right of that you have 50%. So actually that's what the median is. So this is the median, or this is also 50th percentile. So these are some of the measures of numerical measures of location, which tries to tell you like where most of the values are concentrated, or how the overall data is divided into different maybe percentiles or quartiles. Another thing which we are interested in is the variability or the spread. So location gives you only part of the information about the data. It only tells you where the center of gravity of the data is, where most of the values are concentrated, but it does not tell you how much variability exists in the data. So for that we need numerical measures for spread. So one of the commonly used or most commonly used measure of spread is range, which is maximum minus minimum. So you have any data set, you find the maximum, find the minimum, and that's the range. For example, suppose you have 2, 1, 5, 3, 9, and suppose this data is in centimeters. So maximum is 9, minimum is 1. So range is 8 centimeters. Although this is easy to use and easy to understand, but it is only based on two data points, the two extremes, lowest and the highest. A range does not care what is going on in between. So for example, between 9 and 1 you have so many different values like 2, 3 and 5. So if 5 is 7 or 3 is 4 or 2 is 8, it does not matter. Range remains exactly same. There is another measure which uses information from all the data points, and in fact that calculation, because it has become a standard throughout the world for capturing spread or variability in the data. So this method of summarizing data spread in numbers is called standard deviation, which is very popular and very commonly used. So let's say this data is represented by some random variable x. So x is a random variable, means it could be length, height, and because it can take values randomly, like in this case 2, 1, 5, 3, 9, so it can take any value, it is called random variable. To calculate standard deviation, we create another column called x minus x bar. X bar is the average, whole square. And then we total this column or add the column. But before we can calculate this column, you need x bar, so calculate x bar. So add all the values, divide by 5, you will get x bar. So in this case, x bar is 4 centimeters. 2 minus 4 whole square. Now standard deviation is given by square root of this number that we got, 40, and divided by sample size minus 1. So we have 5 data points and then minus 1. That will give you square root of 10, which is 3.33 centimeters. So that's the standard deviation based on this data. Let's say I have another data set and I'm making this data set less variable. So let's say we have 2, 1 and 4, 2, 1. So you can see that there's not much variation compared to the previous data set. And let's see if standard deviation comes out to be lower. If you average this, you'll get 2 centimeters. You can see compared to this, it has come down, and that is very visible from the data also. Like you can see this is less variable compared to this data set. So standard deviation will be more when there is more variation in the data, more spread. It will be less when the variation is less. So square root of, we did x minus x bar whole square and we added them in the numerator. So for adding, we have a symbol like this. So this means add everything that comes in front of it, and then we divide it by sample size n, small n, minus 1. So this is the formula for standard deviation. Now because in the numerator you have x minus x bar whole square, this cannot be negative. So standard deviation cannot be negative, and the lowest possible value is 0. If there is no variation in the data, it will be 0. So standard deviation is greater than or equal to 0. In the denominator you have n minus 1. So because this is n minus 1, standard deviation can be calculated only when you have sample sizes greater than or equal to 2. If you have only one sample, so n minus 1, so 1 minus 1 becomes 0, and standard deviation in that case is not defined. So it can be calculated only for n greater than or equal to 2. So generally, if you have population and sample, so standard deviation for the population is represented by a Greek alphabet sigma, and for sample small s. Now there is another term called variance. So variance is square of standard deviation, so sigma square, for sample it is s square. So if you have variance, to get standard deviation, you simply take square root. Now we have looked at several measures for location and standard deviation. X bar and sigma or standard deviation are most commonly used location and spread measures. So in fact there is a measure called coefficient of variation which combines the two. So CV equals standard deviation divided by X bar times 100. So this is in terms of a percentage. Now this is used when you have two data sets which are totally different in terms of numerical values. They are quite different. So let's say we have data on stock price of Apple and Microsoft. So these are the closing prices in the stock market. Closing prices are the prices at the end of the day. So you can see that the numbers for Apple are quite big compared to, even more than 10 times compared to the numbers for Microsoft. Apple varies in like more than $1, and you have minimum value 343, maximum 52, so that is 7 plus 2 9, so $9 variation within these 5 data points. And obviously in Microsoft you do not see a $9 variation, so the variation looks much smaller because actually the numbers themselves are much smaller. So obviously this is not apple to apple comparison because of the size of the numbers are totally different. So to make a comparison of these two dissimilar data sets, coefficient of variation can be used. So what we do is you calculate X bar, calculate standard deviation for the two, and then using the CV formula you can find the two numbers. So you can try that and you should get CV of 1.02 for Apple and 0.82 for Microsoft. So it just happens in this case that coefficient of variation indicates that there is a larger value for Apple. That means compared to the two, in fact Apple does show more variability. Interpretation of this 1.02 is another numerical measure which combines X bar and sigma is z-score. So this is also called as a standardized value. The formula is given by z is equal to x minus x bar divided by standard deviation. So by doing this calculation or transformation for z, you can say mean is 0. Mean is always 0. Standard deviation is always 1. So that's the property of z. Suppose you have 10, 20, 12, 17 and 16. Now to calculate z values for this, you first need to calculate x bar and standard deviation. So sigma is 4 or standard deviation is 4. So now I can calculate z. Z equals x minus x bar, it is divided by s. So x is 10, x bar is 15 divided by 4. So this will give me negative 1.25. So a negative value indicates that particular x value is less than the average. So 10 you can see is less than 15, so less than average. And a positive z value indicates that your x value is more than the average. And the further z value away from 0, that means further away x value is from the average. So basically it indicates location of each data point with respect to average. So one application of z-score, it is in the form of a well-known theorem and a very simple theorem it is named after a Russian mathematician. So it's called Chebyshev's theorem. It says at least 1 minus 1 over z square of items in any data set will be within z standard deviations of the mean. The only condition is that z has to be more than 1. So this theorem applies to any data set in the world, and let's say z equals 2. So when z is 2, 1 minus 1 by z square, you get 1 minus 1 by 2 square. So 1 minus 1 by 4, which is 3 by 4, or 75%. So now if you reread this theorem using this number, you can say at least, so 1 minus 1 by z square is now 75%. At least 75% of items in this data set, where z is 2, will be within 2 standard deviations of the mean. So this is the interpretation, and because it refers to any data set, that means whether your data is skewed, like if you have positively skewed distribution or a negatively skewed distribution, it hardly matters. In fact, because it says at least, so the least value you will get is for skewed distributions. If your distribution is like symmetric, like this, then obviously this value, this percentage will be more than 75%. So for symmetrical distributions, it will be more than this number. Theorem only gives you the lowest possible value for this percentage, and in reality, the number could be more. So empirical rule relates to a symmetric histogram. So you have something like this. So if your data is captured like this, where it shows a symmetrical pattern. So in the middle you have the average x bar, and as you go towards the right or left, so suppose this is x bar plus 1 standard deviation, x bar plus 2 standard deviation, x bar plus 3, and same thing on the other side. So obviously it will be minus. So empirical rule says that if you go 1 standard deviation to the left or right of the average, which means these two data points, this area, the area covered by plus minus 1 standard deviation, is 68.26%. Now if you go one more standard deviation away from the average, as captured by these two lines, so this will cover, obviously this will cover more area than 68%, and in fact this covers 95.44%. And if you go to plus minus 3 standard deviations, which is this line, so this will cover even more data points in the entire data set, and in fact this will cover 99.72%. So very small percentage is beyond plus minus 3 standard deviations. So when Chebyshev's theorem said, like when z equals 2 means you are 2 standard deviations away from the average, so it covers at least 75%. But in this picture you can see plus minus 2 standard deviations, so this is covering as high as 95.44%. So Chebyshev's theorem gives you the lower bound and empirical rule gives you the upper bound, for that range, like how much of data is covered. So it cannot be more than 95.44% and it cannot be less than 75% in this case. If you take another example, let's say z equals 3. Using Chebyshev's theorem, you can calculate 1 minus 1 by 3 square is 1 by minus 1 by 9, which is 8 by 9, and this is about 88.9%. So Chebyshev's theorem says that at least 88.9% is within plus minus 3 standard deviation. But if the pattern is symmetrical, as in the case of empirical rule, so it can go as high as 99.72%. So overall, it cannot be less than 88.9% and it cannot be more than 99.72%. Number 7. Use Chebyshev's theorem to calculate percentage of individuals who sleep between 4.5 and 9.3. X bar and S, standard deviation. So let me make a picture. We have 6.9, 4.5 and 9.3. So suppose this is represented by a variable x. So what we need to do is we have to convert this x into z, and the formula is x minus x bar by s. If you convert this into z, it becomes 4.5 minus average 6.9 and standard deviation 1.2. So average and standard deviation, as you know, is given. So this comes out to negative 2. Do the same thing for this number in which we are interested, and you get 2. We get plus minus 2. So basically this means z is 2. So generally in these problems you will have this symmetrical pattern. So if you get negative 2, the other one will be positive 2. If you get negative 2.5, the other one will be positive 2.5. So z equals 2 means 1 minus 1 by 2 square, 1 minus 1 by 4, or 3 by 4, or 75%. We have seen z equals to earlier also. So we can say at least 75% of the individuals sleep between 4.5 and 9.3 hours. So you can say at least 84% of individuals sleep between 3.9 and 9.9 hours. Now another application of z-score is for detecting outliers. Outliers are data points which are unusual. So for example, let's say you are looking at some kind of car failure data, and you have like thousands and thousands of data points, and you come across a car which has been driven for like 3 years, and the data shows that it has been driven only for 20 miles. So 20 miles in 3 years obviously looks very unusual. So obviously there could be some mistake by a person who was entering the data in the system. So these kind of errors, especially when you have like lot of data points, can always occur. If you include such data points in your analysis, so sometimes you may not be able to get proper estimates, or you may not be able to do a proper analysis if there are a lot of errors like this. Some simple things one can look at is if z is less than negative 3. So if you calculate z values and you find the values are less than negative 3, that is indication that the data point is unusually small, like 20 miles in 3 years. So that is very, very small data point. Or if you get something unusually large, like greater than positive 3, maybe something like in 2 days, like some error, you see that it has been driven maybe 2 million miles. So 2 million miles in 2 days obviously is very, very large. So this data point will generate a z value which is much bigger than plus 3. Detecting outliers using z is a very common practice. Now another way people like to look at numerical summary is 5-number summary. Those 5 numbers are, and this data is also sometimes represented graphically in the form of what is known as a box plot. Let's say we have some items with random variable x, maybe tea packets, and the average is about 100 grams. So if you see a box plot like this, so there is a box or rectangle, and there could be a line in between, and you also have this extended left and right. So this particular point is 1 minimum. This particular point is 2, which is first quartile. This line in the middle of the box is 3, indicates median, and 4 is the third quartile, and this data point is the maximum. So obviously when you have thousands of data points, calculating average using a calculator is going to be very, very tedious. So a better way is to use Excel function. So whenever you want to use Excel function, always start with equal sign. And to calculate average, simply type average. Type average, and then within the brackets you have to refer to the data. So I'm going to show you how to do that. So you can use this for average. Similarly, if you want median, type equals median and then refer to the data. So suppose I want to find out average material cost. So I want to find the average cost based on this column. So I can type equals and then average, and then we have this bracket, and then you select, if you click on column F, so don't click on material cost, click on F and the entire column will get selected. So close the bracket and hit enter. That will give you the average. So average material cost for this data is $179.39. You have like 1624 data points and you can calculate average within a second. Similarly, if you want to find the median or the middlemost value, start with equal sign and type MEDIAN median and start a bracket, and again select the entire column just like we did earlier, and then close the bracket, hit enter. You have the median. You can use the same idea for mode and so on. In fact, equals and then percentile, and then you start a bracket. Array means data, so you click on this column again, and then you can also see that it gives you the style of writing this function. So after array there is a comma. So once you hit comma, you will see that K gets highlighted. K is which percentile. We have to specify which percentile we are interested in. So if we are interested in 10th percentile, we cannot write 10. We should write 0.10. That's what it will understand. 0.10 to refer to 10th percentile. Close the bracket, hit enter, and that is 118.36. So that is the 10th percentile. You can also change, instead of 10 you want 90th percentile, so 0.9. So hit enter, that will be 90th percentile. Similarly, let's say you want to calculate standard deviation. So the function to be used is stdev and then bracket. So again select the entire column and close the bracket, hit enter. That's the standard deviation within no time. Key functions that you will find useful: stdev for standard deviation,